Hi students, welcome to my lectures on thermodynamics. In the last class, we have discussed about how to find out enthalpy of a reaction at any temperature. In that formula, we have one term which is called IDCPH because it has given the name. Okay, if you know IDCPH, you can calculate the enthalpy of the reaction at any temperature. What is this IDCPH and how we can evaluate this term to find out the enthalpy of reaction? That is what we will be discussing in the today's lecture. If you see the term IDCPH, it is T0 to T integral del Cp by R dt. If you know this integral term, you can evaluate the IDCPH. What is del Cp? As I told you that in a reaction, example A plus B gives rise to C plus C, there is some reaction is happening. The del Cp term is denoting specific heat capacity of the products minus the specific heat capacity of the reactants. If you do this term, if you evaluate this term minus products minus reactants, then this del Cp will turn out. To evaluate del Cp, you should know what is Cp. And you know the Cpi of any component by R is A plus B T plus Ct square plus dt power minus 2. So every component involved in the reaction comes with some terms, some constants. Okay, this A, B, C, D are the constants for that particular reactant or a product. That means if you know the del Cp, which is nothing but sigma of Vi Cpi. Vi means in a reaction, Vi is denoting the stoichiometric coefficient of that particular reactant or product. If there are four, that means there are two reactants or two products, the summation of all, which is nothing but del Cp. Okay, and if you know the Cp, you know the Vi, that means stoichiometric product of the reactant, then you substitute in this particular sigma term, then you get a del Cp. Example, there are four reactants. A, B gives rise to C and D. Example, Va into Cpa plus Vb into Cpb plus Vc into Cpc plus Vd into, maybe in the new D into Cpd. If you summate all these terms, then you get del Cp term. Every Cp consisting of these four terms, A plus Bt plus Ct square plus dt power minus 2. So once you substitute this all the Cp information in this formula and you get this big term. Okay, that means IDCPH, once you substitute the value of del Cp in this integral and evaluate the integral, then the final expression comes like this: delta A into T minus T0 delta B by 2 T square minus T0 square plus delta C by 3 into T cube minus T0 cube and delta D into T minus T0 by T into T0. T is the temperature at which you wanted to evaluate. T0 is some base temperature. That means T and T0 denotes these two temperatures. Okay, what is this delta A? Delta A is nothing but sigma Vi into Ai. Delta B, that means sigma nu I into Bi. Delta C, sigma nu I into Ci. And delta D, okay, this is D, okay, delta D. Because every term, every component consisting of this A, B, C, D terms, so that is why you have to evaluate delta A, delta B, delta C and delta D. All this delta wherever you see, that means we are thinking about products minus reactants. That is what this delta representing. Delta A means what are the A, because every component consisting of A, B, C, D everywhere. Because once you go through this example, you will understand what is this terms is. Let us move ahead. Okay, if you know this term, that means you know IDCPH. In other formula, if you common out T minus T0 in this particular term, if you common out T minus 0, then the remaining terms means delta A plus delta B by 2 into T plus T0 plus delta C by 3 into T square plus T0 square plus T T0 plus delta D by T into T0. That means if you have already common out the t minus t0, the remaining term in this bracket is denominated as MDCPH. This entire term is called IDCPH. If you somehow simplify it more, then this ICPH is nothing but t minus t0 into MDCPH. IDCPH is nothing but t minus t0 into MDCPH. What is this MDCPH is there in the bracket. That means to evaluate this term, either you can use this formula or you can use this formula to calculate this IDCPH, because once you know the IDCPH, you can calculate the enthalpy of a reaction at any temperature. Okay, that is what here it is written. IDCPH is equal to MDCPH into t minus t0. Once, if you remember this formula in the earlier lecture, the enthalpy of the, because all the agenda for this lecture is to find out this particular term which is called enthalpy of the reaction at any temperature. The enthalpy of reaction at any temperature is equal to enthalpy of the reaction at some known temperature plus R into IDCPH. This IDCPH is nothing but MDCPH into t minus t0. Either you can use this formula to evaluate delta H, or you can use this formula to evaluate the delta H. So presently we are going to use this particular formula to calculate the enthalpy of the reaction at any temperature. Example, so it will be more clear. CO plus 2H2 gives rise to CH3OH. This is the reaction. You have to find out the enthalpy of this reaction at 1073.15 Kelvin. So you have to evaluate. Given enthalpy reaction at 298 is equal to minus 90135 joules. You have to apply this formula to calculate this particular term given this and this. I know T is nothing but 1073.15, T0 is nothing but 298.15, delta H reference temperature is minus 90135 joules. Given everything, you have to find out this particular enthalpy of a reaction. For this reaction, let us denote CO as A, hydrogen as B, CH3OH as C. Okay. The stoichiometric coefficient of A is 1, stoichiometric coefficient of B is 2, stoichiometry of the coefficient of C is 1. That is why VA is minus 1, VB is minus 2, VC is 1. Because we have to take the stoichiometric coefficients of reactants as a negative, stoichiometric coefficients of the product as a positive. And you can see here, what is delta A? Sigma VI into AI. VA into AA plus VB into AB plus VC into AC, because there are three components involved in the reaction. So that is why we have to expand the sigma to these particular three terms. AA and AB and AC are constants of reactant A, reactant B and reactant C. Similarly, delta B, delta C and delta D. So where we are going to form, because there are a number of tables available for the every particular reactant, we have AA, AB, AC and AD. Everything is available. Okay. Example, if you see this table, VI, that means stoichiometric coefficients. For a C is minus 1, for A and B they are minus 1 and minus 2. The AI, that means constants of C, that means AC, AAA, EAB, BC, BA, BB, CC, CA, CB. Okay, the DC, DA, DB. All the constants are given for all these three reactants. Okay, once you evaluate this delta A, how you can evaluate? Using this formula, VA into AA plus VB into AB plus VC into AC. VA, this is VA into AA plus VB into AB plus VC into AC. Similarly, you get delta A, okay, minus 7.663. Similarly, you can see this is VC into VC, like that. To expand this delta B, you have to see these two. This into this plus this into this plus this into this. Similarly, you have to calculate for delta C and delta D. Once you know the delta A, delta B, delta C and delta D, you can use this particular formula to calculate MDCPH. So MDCPH is minus 2.084. Therefore, delta H of the reaction is nothing but delta H 298 plus R times MDCPH into 1073.15 minus 288.15. So once you substitute each and every value, you get delta HT, which is minus 10.3566 joules. That means if you know the delta H at 298, you can calculate the delta H at 1073 Kelvin. So this is how we have to use this particular IDCPH evaluation to find out the enthalpy of the reaction at any temperature. Thank you. I hope you have learned. Let us meet with the new lecture.